Okay. Simulating state response 2.4. And this is, this ahem is there, so I just put a footnote. The source for this lecture is right there. It's an M file. So I published this as an M file, so you can just pull this in and run the script. Yeah, so no secrets here. The source is online. You can go ahead and download that if you want. And if you have MATLAB, pull it up and you can play along if you'd like. But you don't have to do that. And I gave you guys all the notes. There's no fill-ins here, but I'm going to just like scratch on the side and stuff, and you guys can write on them your own notes. I just realized I forgot to put the B, C, and D matrices on this part, but that's okay. You guys will forgive me. So what we're doing here is we've learned in this chapter how to solve for the response of a state space system, right? We model a system in state space form, and we can actually solve that now. We have an expression for it. It involves an integral, so it's not like it's completely solved for us. We still have to integrate. But in theory, for anything we can integrate, we can solve. Now, this lecture is kind of my attempt to show you guys all of the ways that one might begin using MATLAB to use or to solve these types of systems, to use the state space capabilities of MATLAB. And I'm going to kind of do two different tracks in this lecture, and we'll kind of see some advantages and disadvantages of both of them and compare them. So that's what this is, and a lot of so this lecture, we're mostly using numerical techniques, but we're also going to use the analytic technique that we solved for, but we are going to numerically integrate just because we're using MATLAB, and doing anything in symbolics in MATLAB is hard. Not impossible, but hard. So I don't like using MATLAB for symbolics, so I even though we used the Analytic Solution as part of this lecture, I'm going to show you how to use it in a sort of numerical way, in addition to the pure numerical solution. So this lecture requires you have the control systems toolbox for MATLAB. The first part doesn't, but later on, the numerical part does require you have the control systems toolbox. MATLAB has several built-in functions and control toolbox functions for analyzing state space system models, especially linear models. I'm going to explore a few here. You can also do nonlinear models, but they don't have as many tools for that. So consider, for instance, a linear state space model with the following A, B, C, and D matrices. I just did A, and then I just switched over to the code, apparently, is what I did there. I thought I had gone back and put B, C, and D, but I forgot. So here's our A matrix. B, C, and D matrices are there. So let's, just from looking at this, so these are MATLAB defined A, B, C, and D. What are we working with in terms of system order? Third order? Yeah. So third order system. The order is n, and the A matrix is always an n by n matrix, so it's a third order system. And then B is going to give us some insight into how many inputs we have. How many inputs do we have? So the B matrix, so this MATLAB syntax is that if you use a semicolon in between elements, then you're defining a new row. So the B matrix is 0, 1, or 1, 0, 1. So remember, in our state equation, B multiplies the U vector, right? So the inner dimensions must agree. So it's a 3 by 1. So how many inputs do we have? 1. Very good. And then how many outputs do we have? 2 outputs, because we have 2 rows in our C matrix, right? So there have to be 2 outputs. Okay. Good. So for a step input of 3 US, an initial state, this is a row vector that's transposed, it's a column vector. So we say that the initial state of the system is 1, 2, 3, because I had to make something up. That was something I came up with. I know, it was really random, the 1, 2, 3. So 1, 2, 3 is the initial state, and we have a step input of 3 times a unit step. Okay? Let's compare the analytic and numerical solutions for the output response y of t. So I defined here what's called an anonymous function, okay? And it's a function of time. And I wrote this function like this. The first time I wrote this function, I just wrote it as 3 and just assumed any time you put in there, it would return 3. But then I was like, you know what I want? I want to be able to put in a time vector to this and have it return a 3 for each value of time also. So that's why I wrote it like this. Size of t returns the dimensions of the t vector that's put in. And if it's just a single, if it's just a scalar, it's just a 1 by 1. And then ones is a function that returns a vector of ones, or an array of ones, the size of whatever you tell it to do. So this is a little trick to generate an array of whatever size something else is. So ones the size of t gives us a vector of ones, the same dimensions as the t vector. And then you multiply it by 3, the scalar, and so there's just an array of 3s, the size of the t vector, and it returns that. So that's handy later on when we're going to use that in the simulation part. So they'll come in. But you can always just plug in time equals 17.6, and it'll return 3. So, okay, and then the initial condition as well. So the first section is actually the analytic solution, and it takes a lot longer than the numerical stuff. So you might think, so after we go through this analytic solution, you might think, oh man, MATLAB, it's hard to solve this stuff in MATLAB. But that's just for doing it this sort of analytic solution way. At the last section, we're going to do the numerical way. We'll use their built-in functions, and it's like 3 lines, okay? So we're using our analytic result, which is a rearranged version of equation 210, in this first section. So we want to use this result because this is the solution already. We just need to plug things into it and evaluate them. The evaluation of this is a little tricky though because we have this integration. And if we wanted to do this in a purely analytic way, we would find phi as a function of time with its exponentials in it and everything. And then we would integrate each element of the integrand here. But like I mentioned before, numerical stuff is much easier to do in MATLAB than analytic stuff, or than symbolic stuff. So we're going to use this expression, this analytic solution expression, but we're going to use a numerical integration technique to evaluate this integral. And that's all we're doing here. Okay, so first thing we need is the state transition matrix phi. So we consider the eigenproblem. Remember, our preferred method of finding the state transition matrix is by finding phi prime, the state transition matrix for the diagonalized system, right? Because that was a lot easier than having to recognize the series in the other method. So we need a state transition matrix. So we'll use this eig function in MATLAB, which returns the modal matrix and the lambda, the eigenvalue matrix. So you just say m comma l equals eig of the A matrix, and it just spits these out. And what strikes us first about m and l? Complex. Yeah, so these things are complex, which I warned us, that can happen, right? They're not always real like they were in the example. So this is an example of one where they're complex. The first eigenvector actually appears to be real because there are a bunch of zeros over here in the imaginary part. But the second and third eigenvectors have some substantial imaginary parts to them. And the same with the eigenvalues, right? So -3 is the first eigenvalue, real. And then we have -0.5 plus or minus 4i, or J4. So that's approximately 4. So those are our eigenvalues, and these are eigenvectors. Kind of nice that MATLAB just does that for us. But we could find that by hand as well, and remember, we do need to be able to do that. But it's nice to be able, when you're doing your homework, for instance, just pop it into MATLAB and just check yourself, make sure you're getting the right answer. So that's a nice thing. Note that when assigning its output to two variables, m and l, the eig function returns the modal matrix and the eigenvalue matrix. The modal matrix of eigenvectors m has each complex, or each column or eigenvector normalized to unity. So notice that these are all unit vectors. These eigenvectors are all unit vectors. And that's just MATLAB's standard way of normalizing them. Remember, we can scale these by anything we want. This could be 17. This could be, like, you could multiply this whole thing by 26, and it would still be an eigenvector. So that's something to keep in mind. Also note that they're complex. And finally, since the real parts of all the eigenvalues are negative, the system is stable, right? So we look at the three eigenvalues right here, all along the diagonal of this eigenvalue matrix. And the real parts are -3 and -0.5 and -0.5. And remember, the eigenvalues are the same as the roots of the characteristic equation, which determine the stability of a system by the sign of their real part, right? If the sign of the real part is negative, we're going to have a stable system. So by just looking at the eigenvalues, we can determine stability for the system. And we can determine that this system is stable, which is good. Good news. So, in order to convert to the diagonal basis state transition matrix, or in order to take this result and construct the diagonal basis state transition matrix, we just need to do e to the lambda t, and I'm going to define that as an anonymous function, phi underscore p for phi prime, and I'll kind of explain with this. These diag functions. So you might look at this and say, why didn't you just do x of L times t? And the problem with that is what MATLAB does is it does an element-wise exponential of L times t, which is fine for the diagonal ones. It's exactly what we wanted. But e to the 0, remember this is supposed to look like e to the lambda 1 t, e to the lambda 2 t, e to the lambda 3 t, with everything else being zeros. So along the diagonal, if you just take e to the lt, you have exactly what you're looking for. But along the off diagonals, we have e to the 0, which is 1. We don't want 1 out here. We want zeros out here. So what I did is a little trick here. You could do it. You could like construct it with a for loop, for instance. That would be fine. And if you, at first I thought that was what I would do, and then I was like, no, I could be tricky instead. So I decided to be tricky instead. So diag is a function that does, it's kind of a weird function. If you hand it a matrix, it returns to you the diagonal of the matrix as a vector. If you hand it a vector, it returns to you a matrix with that vector on the diagonal and zeros elsewhere. Okay? So what I do is I say, x of lt is what I want along the diagonal, so I'll use diag to extract that diagonal, it's just these guys, from it as a vector, and then I'll turn around, hand it back to diag as a vector, and it'll construct it as a diagonal matrix with zeros elsewhere. So this is tricky. I like that move. That was fun. So I think I chuckled to myself when I wrote this. You guys, my life is really interesting. Okay. Okay, the original basis state transition matrix phi is what we want, right? So phi prime is great, but what we really want is phi. But last lecture, we derived this really nice expression for phi in terms of phi prime and the modal matrix M. And so we define a function where we do that conversion for any value of time. Now, I did this little efficiency thing here. So if I call phi a bunch of times and I stuck in M inverse, I could have just put M inverse right here instead of having to do 2 steps where I compute M inverse and then plug it in. But then every single time I called that function, it would have to do that matrix inverse, right? So instead what I did is I had it do the matrix inverse once beforehand, and then I stuck it into the function. So that every time it calls the function, it doesn't have to recompute that matrix inverse. It can just pull in the variable that I've had defined as the matrix inverse. So it's quite a bit more efficient if you're going to call this function a lot. So that's what I did. This script is definitely not intended to be super efficient, but I just wanted to, I know you guys are still kind of learning how to program and how to write code in MATLAB. So showing you guys little tricks every once in a while I think is, useful. You learn one trick at a time. So yeah, so whenever you define a function and you've got the same thing in it that you have to do over and over again, if it's something you can compute beforehand, before you know what the arguments of the function are, just once outside the function and hand it to it, that's much, much better than having it inside the function computed over and over again. So, okay, so the free response. So we've got our state transition matrix phi, and so the free response is relatively straightforward to compute. Remember that the free response is just equal to C phi times the initial state. That's the first term in that total solution. So if we look back here, that's this term, right? This is the free response. So we're just going to use that, and we'll find the free response. We could, do it all at once, but I thought that the forced response is a little tougher, so I thought we would just pick the low-hanging fruit while we have it, and then we'll build our way up to the forced response. So the free response, it's a little bit, oh man, it's bright in here. Can you guys see this? Could somebody close some of those blinds maybe? I think it would help. I mean, I know that you guys could probably use some sunshine in your lives, but we don't have time for that. That's a little better, huh? Okay. Thank you. Okay, so what we're going to do is we're trying to construct a solution at a bunch of values of time, right? And so even though we're looking at an analytic solution, we're looking at the analytic solution in a sort of pseudo-numerical sense. We want to plot it at a bunch of points. And so we're going to compute it at a bunch of points. And those points are going to be defined by this TA vector. And the spacing always gets weird, and I bring it into the Illustrator for whatever reason. But this is 0, 0.05, 5, which is to say a time vector that goes from 0, time equals 0, in increments of 0.05 up to 5. And we'll always use seconds for our time unit. And then I do this sort of fancy thing here when I initialize the free response array. But let's think for a moment what we want this array to look like in the end. We have two outputs, we decided, right? And so we're going to want to compute those two outputs at each value of time. Now, at time equals 0, time equals 0.05, etc. So we can construct an array that is a 2 by however many points TA has, 2 by length of TA, that gives us those two outputs at each time step. Okay? Which makes total sense. And so to do that, so to initialize it, it's good to initialize an array, even though MATLAB does not make you initialize an array. Why? Does somebody know why we do it? It's more efficient, because if you don't do that, then MATLAB won't put an array in memory in a sequence. It'll have to just like store it in different places. And if you don't pre-allocate a certain chunk of memory for it, then it's spread around and it's less efficient to access. So that's why we pre-allocate. It's also a good check on ourselves. Like, does this make sense? Like, are we putting the values in this array correctly? Is this something that I want to be doing? And another way that I sort of use to check myself is that I pre-allocate not with zeros, which is typical to do is with zeros. I pre-allocate with not a numbers, NaNs, because if you get to the end and you have any not a numbers left in your array, it's a lot easier to pick those out than zeros, to recognize that you never wrote onto that. So that's why I do that. So what I'm doing here is I'm saying, okay, I want to generate an array of ones, and the dimension of that array of ones should be the size of C, the first dimension of C, which is the number of rows in C, which is the number of outputs, okay, by the length of the time array. So I get an array that looks like two values at a new time, two values at a new time, two values at a new time, etc. So that's what I'm looking for. And then they're all ones, and then I multiply it by nan, which makes all of them nans. Because nan times 1 is nan. Did anybody call their grandma Nan? Never. I called mine Nana, so. Not Nan, though. Okay. So then we're ready for our loop. So we're just getting ready for the loop. We hadn't even got to the loop yet, but now we're ready for the loop. So for I equals 1 to the length of the time vector, which means, so for each value of time that we've prepared, let's evaluate what the output is. Okay? So we have the formula right here. So the C matrix times the phi matrix evaluated at that time, right? So you take the time array at that index, gives you the value of time. You give it to the phi function, which returns the state transition matrix at that time. And you multiply that by the initial condition, initial state condition. Okay? And then you go through that loop several times. Free response. I'm going to print it out. The spacing is weird again, but this is a colon and then comma, and then it's 1 through 3. So it's all rows and then columns 1 through 3. I want to print out. I just do this so that we can just check to see what it looks like without being overwhelmed by 20 pages of output. So I'm seeing numbers come out here that are, first off, it's a 2 by 3 that we printed. And as I would expect, these are coming out real, right? The imaginary part looks to be 0, which is good because we expect our solution to end up being real. Even though we're in the intermediate using complex numbers, the values at the end should be real. So a time array TA was defined such that phi could be evaluated. The first 3 columns are printed. Note that there's a hanging chad of imaginary components. You guys may be too young. Anyways, hanging chad. Back when politics wasn't so fun. Or maybe it was just, it was back when we were innocent and thought the world could still be a better place. Yes. When elections turned on hanging chads instead of Russia. Anyways. Okay. So, before we realize them, so what we're going to do is we're going to say, oh, these imaginary components are small. We just get rid of them. Okay? But we should really make sure that they're negligibly small. So what I'm going to do is take the imaginary component of each of these values, and I'm going to take the absolute value of it, and I'm going to take of each of the values, and I'm going to take the maximum. So what the max function does is it chooses, in MATLAB, I don't even remember if it takes the first dimension or the second dimension by default, but it maximizes, it finds the maximum value in either a row or a column. And I don't even care which one comes first, because I'm going to take the maximum of those. I'm going to find the maximum absolute value of an imaginary number in the entire array. And I'm going to print it out. And it's 5 times 10 to the negative 16. So it's super small. And so we can reasonably discard the imaginary part. This was just a check. I mean, I knew that it was supposed to be that way, but it's just a check to make sure that I didn't screw something up. And it is actually small. So that's good. So we checked it and it checked out. So then we can just take the real part of the array. And the real part that's remained is plotted in figure 2.1. So that's what we've got right here. So we start out with these initial conditions, and we have no forcing. Remember, the free response is for no forcing. No forcing. Y1 has this nice oscillation down to 0, and then Y2 also has this oscillation down to 0. And you guys, so when you make up problems like this, you pretty much just tweak the numbers till like the plots look pretty, okay? I came up with this problem. The eigenvalues came out to be nice things. I was like, you kind of have an idea of where they might be based on where you put numbers in the matrix, but kind of lucked out, and they were like nice, and I was like, oh, cool, but surely I'll need to tweak it for the plots to look good. Beautiful. And I was like, you know what? Today's my day. Did I mention that my life is really interesting? Okay. So this is, we get these damped oscillations, right? And which is what we expected. It's a stable system, but also we had complex eigenvalues, so we kind of expected there to be some oscillation involved. If they were totally real, we would expect just exponential decays, right? But since they were complex, we expected this oscillation. So nice. So we got this. Actually, it wasn't that painful to get that. It was relatively straightforward. And so the MATLAB M file has the plotting routines in there. I didn't include them in this because they were super repetitive. I have 5 plots, and it's like the same code 5 times. So they're in the M file though. What?
Why not just put in a loop, have it run?
Because I wanted to intersperse the graphs as we go, so they're not all at the end. It's the forced response. Now, there is the matter of integration in equation 223. So to find the forced response, we're looking at, way back here, our analytic solution has this part that's all the forced response, right? Our D is 0, so this is just gone. So really we just have this integration. So in order to compute this, it's similar. You have to know phi and whatever, but you also have to do this integration. And that's the trickiest part to do this. And like I said, if we wanted to do this sort of completely analytically, we should actually write out the functions, integrate the functions, get analytic expressions of those integrals, and that would be the completely analytic way to do it. But since we're in MATLAB, and that's kind of hard to do in MATLAB, I mean, you can do it. It's doable. Last year's MATLAB example, I did it in MATLAB with Symbolic Toolbox. But anyways, I shudder at the thought. I recommend, if you're going to do that, and you don't want to do it by hand, I recommend using Mathematica to do the integrals, or, Wolfram Alpha does the same thing on the internet, or SageMath. It's like an open source version of Mathematica, essentially. Yeah. So I don't think I'm going to do a lecture on how to do it in those other programs, but I might post an example. I've done some in Mathematica in previous years. I might post a Mathematica example. Okay, cool. So we're way over here. So the forced response, we want to compute that. But we have to integrate. Since MATLAB doesn't excel in symbolic integration, we're going to avoid to write the solution symbolically. For this reason, we choose a simple numerical approximation of the integral using the traps function, which is trapezoidal integration. So this is back to Calculus 2, I think, right? Calculus 2, where you learned how to do integration. And the first way you did integration is approximating an integral by finding areas of trapezoids. Right?
Riemann sum?
Yeah, Riemann sum.
It's a little different for trapezoid.
But I think you use the summation.
When you had an infinite number of them.
You draw trapezoids.
Yeah, so if you have close enough points, then it approaches the integral, right? So that's what we're going to do, and in MATLAB that's pretty straightforward. But I think it's a little bit tricky. The tricky part is sort of conceptually, what are we integrating over, and evaluating that at each point in time. So I'm going to actually evaluate the integrand first, which is not necessarily the most efficient way to do it, but I thought conceptually this was an easier way to do it than the alternative. So the integrand, I initialize that by saying that it's, once again, 2 by the number of length of time, right? 2 by that. And so we need to find what the integrand is for the 2 values of the vector that the integrand comes to. So the integrand, if I go back to it, over here, the integrand is this. And this ends up being a 2 by 1 vector. So I need to compute that 2 by 1 vector for each value of time. Okay? And then we'll do the integration part in the next step. We could have done them in one step, but I do think it's a little tough to follow that way. So, once again, I loop through each value of time. And in order to call out the fact that I'm integrating, or I'm my integrand is in tau instead of t, I just said tau is equal to the current time value, which was sort of superfluous, but I thought it was a little easier to look at. So tau, I evaluate phi of minus tau times b times u of tau, and which gives me the integrand, which gives me 2 values, and I can put it in my array. And then the next time step, I get 2 more values, go around and around and keep computing it. So I keep computing the integrand at each time step. Then I can numerically integrate. So my integral, I ended up pre-allocating to zeros in this one, and I don't remember why I chose 0. Oh, it's because it's sort of a silly reason. When you do this, you end up you can't numerically integrate 1 point. You can't find a trapezoid that approximates the area under 1 point. So you have to have at least 2 points. So anyways, I wanted the first value to be 0 instead of nan. It was just kind of being lazy. I didn't want to write a special if I equals 0 in here, or I equals 1 in here. So in any case, I here is the upper limit of integration. I is the index for the upper limit of integration. Once again, we're going through each value of time. We're starting at 2 because, like I said, if you try to numerically integrate 1 point, it doesn't make any sense. You have to, in order to have a trapezoid defined, you have to at least have 2 points, right? So that's why I started at 2. So it doesn't evaluate the integral for time for just the first value of time. It starts at 2. And what it does is it evaluates the trapezoid. The time array goes from 1 to the upper limit of integration index. The integrand goes from 1 to the upper limit of integration index. And so like the first step, we're just finding the area of 1 trapezoid. The second step, we're finding the area of 2 trapezoids, 3 trapezoids, etc. So each time we go through this, we get more. Now you might say, this is inefficient. You're recomputing the trapezoid area for these lower steps each time you go through the loop. And you're absolutely right. This is not a super efficient way to do it. This was the way that looked the closest to the equation. So I tried to do it this way because I don't think that making it super efficient was the point here. I want you guys to understand what we're doing. So yes, each time through this loop we're recomputing this lower one every time, and then after the second one we're recomputing this guy every time. We could have just summed them up, which would have been more efficient. But I thought this was a little bit easier to look at. So, and frankly, I didn't need any more efficiency. It runs just fine the way that it is. So, just a note. Also, the other thing that's a little weird about this is the traps function has a little weird nuance to it. You have to transpose the inputs using this apostrophe here, and then in order to get the output back to the form I wanted, I transposed the output. So it requires that the first dimensions match for whatever reason. So I did that with a transpose. And then I retransposed it back. So nothing magic's happening there. It's just it expected the arguments to be that way. Blue. This connector is like hanging on by a thread. There it is. Okay. Won't touch it. Okay. So now, evaluate the force response at each time. So I've computed this integral, right? So that the integral at each value of time. So now I need to do, just like I did for the free response, compute c times phi times the integral now instead of the initial condition. And I print out the first 3 columns. Once again, it's looking like we have just real parts, but we should check. And once again, the imaginary parts are super tiny. So we don't need to worry about them. We can just get rid of them by taking the real part. The force response is shown in figure 2.2, which once again shows damped oscillations, but for the step inputs, the step input of 3 times the unit step. So instead of starting off with some initial conditions going to 0 via damped oscillations, they start off at 0 and go to some non-zero final values through a damped response, damped oscillation response. Okay. So this is, I think this is all making sense so far. That's what we want to do. And now to find the total response, all you need to do is sum the free and forced responses, right? So it's literally just free plus forced, and that solution is shown here. So it's just the sum of them, y1, you see, starts off with some initial condition, it oscillates and goes to a sort of final value that's non-zero, similar to what the y2 does, but starts at a different initial condition, goes to a different final value. And let's just take a moment to appreciate that this would have been so much work if we didn't have the state space solution. Because if we didn't, we would have 2 differential equations to solve for 2 different outputs. And it would be a mess. And then we would have to get to this final, we'd have to find the particular solution, the homogeneous solution, sum them up, apply the initial condition. Yeah. So it's all kind of mixed in there. We just do it once. We have to do some matrix stuff, but at least we don't have to do it several times for multiple, and do all the steps of these differential equations. So kind of nice. Now we're going to talk about the numerical solution. So the numerical solution of the state equations is rather simple using MATLAB's SS and step or LSIM commands, as we show here. First, we define an SS model object, which is a special kind of object that encodes a state space model in MATLAB. It's literally just the command SS, and you give them your A, B, C, and D matrices. And then you have this magic object assigned to the sys variable. So we could have named it barf or whatever. We named it sys. And at this point, we could use the step function, which would be the easiest way. Because if you want to find the step response for a state space system, there's a really, really simple command called step. And you do step of sys and just gives you plot and everything. You don't even have to plot it separately. It gives you it all. However, that only works for step inputs. So I thought I would show you guys, so you can look up the documentation on step, it's great. Although we are putting in a step input, I thought it would be worth showing you guys how to do a more general input. So with this command, lsim, you can give it so you could be anything. For us, we defined it to just be 3 for all values of time that you hand it, right? But you could define it to be 3 at one value of time and -4 at another value of time and 17 at the next. Totally fine. You can hand this into LSIM and it'll happily simulate that crazy function that you gave it. Doesn't even have to be a function that you could write down in closed form. So yeah, it's pretty cool. Then you hand it a time array. So I just use the same time array, and then an initial state. And it will just happily simulate what you asked of it. So it gave us this value. or this response, which looks identical to the naked eye to this one, right? So, I mean, if I look at these two, I can't really tell any difference between the solution. So this is analytic-based one. It's not purely analytic because we did do numerical integration, but still pretty analytic one. And this is the MATLAB's built-in simulation routines, which took how many lines? Like 3 lines maybe to get? Like super easy, right? Kind of nice. What I want to see is what's the difference between our analytic total solution and their numerical one. And I plot this. So notice that the y-axis here is 10 to the negative 3. So we have some differences between them, and we can call this the error, but it's a little bit unfair to call it the error because we did a numerical integration. If we did solve out analytically, symbolically our solution, and then evaluate it and take the difference from LSIM's solution, that would be a more fair statement to say this is the error. At this point, it's hard to say which one's better because we both did some numerical approximation. So it's something you could play with, but I didn't explore. But the differences are pretty small, but they might be significant for some problems. So it's important to recognize that, and to recognize that it's best if you're if you have this system and like this is your system that you're designing, and you want a really nice model of it, and it's linear, you should just solve it analytically to get a closed form solution. The numerical stuff is great when you're going to play with stuff and sort of do one-off calculations. It's super quick, right? SS, LSIM, bam, right? But if you're going to get really detailed in your analysis and your design, you probably want to find the analytic solution. If it can be found, if it's a linear system. If it's not linear, you can still use some of MATLAB's techniques, but LSIM and SS will not work, at least in this way. There are other ways you can do it for nonlinear systems. Maybe we'll get to talk about that. Anyways, do you guys want to get out a whole minute early? Yep. All right, happy Friday. Don't forget to do the quiz.